Assalamualaikum and hello everyone. My name is Aina Atira from University Science Islam Malaysia. Today I am excited to present my innovation project titled Red Laser Time of Flight Water Turbidity Monitoring System under the Science and Technology category. This project aims to solve the problem of expensive and complex turbidity monitoring tools by introducing a low-cost and IoT integrated solution that uses red laser LiDAR technology to monitor water quality in real time. But first, let's discuss on what is turbidity. Turbidity is a measure of how cloudy or murky the water is, usually caused by particles like soil, waste, or microorganisms suspended in it. It's a key indicator of water quality which affecting not just aquatic life, but also human health, agriculture, and industry. Next, let's take a look on conventional methods of water turbidity monitoring system. And most common tool for measuring water turbidity is turbidimeter. Turbidimeter works by passing light through a water sample and measuring how much that light is scattered by suspended particles. While accurate, these conventional tools have several critical limitations. First, they lack real-time capability. Most turbidimeters require manual sampling and lab testing, which delays results and make continuous monitoring difficult. Second, they struggle with high turbidity levels. Anything beyond 1000 NTU is often unmeasurable. Logically, the most polluted water sources can exceed this limit, forcing users to dilute or pre-treat the sample before testing, adding time and effort. Third, turbidimeters do not store data automatically. Users need to manually record results, increasing the risk of human error and data loss. Second method is by using bathymetric LiDAR. Bathymetric LiDAR is a remote sensing technology that uses green laser light to penetrate water and map underwater surfaces. It's highly accurate and widely used in large-scale environmental or oceanographic surveys. But despite its precision, bathymetric LiDAR comes with three major drawbacks. First, it's bulky, requiring aircraft, drones, or heavy equipment to operate. Second, it's extremely expensive, costing 100 to 1,000 times more than a typical turbidimeter. And third, it needs a complex setup and calibration, making it impractical for everyday use in small or shallow water bodies. That's why a compact red laser LiDAR like mine offers a smarter solution for shallow water turbidity monitoring. In the industry, green laser LiDAR is the standard for underwater mapping, but it's costly and designed for deep waters. While red laser LiDAR, according to optical theory, can also function underwater, though with a shorter range, typically under 5 meters. This limitation can actually become an advantage. Most shallow water bodies, like rivers, drains, and canals, fall within this depth. By utilizing a compact red laser time of flight sensor like the F-mini-S LiDAR, this innovation introduced a new approach to low-cost, non-contact turbidity monitoring for shallow water environment. And therefore, I'll show you introducing the prototype. And the prototype is divided into two parts, which is the chamber and the lid. For the chamber, it has a height of 30 centimeters, which act as a distance of the water samples and LiDAR. Next, we move on to the crucial part of the prototype, which is the lid. On the lid, there is a designated power bank slot, which is exclusively designed according to the size of Penang power bank, which known with its small size and lightweight, with powerful performance, which it can operate up to 48 hours. On the side of the lid, there is a microcontroller casing, which I've placed an ESP32 as a microcontroller to send my data into an IoT platform called Favorion. And lastly, for the highlighted component in the system, which is the F-mini-S LiDAR. It was placed inside of the lid and in the center position, so it can measure water straightly. Next, let's take a look on a video simulation. First thing first, we need to prepare a water sample for this experiment. Step number 2 is to connect ESP32 with power bank. Third step is to place the water sample under the prototype. And lastly, we can monitor the result of the measurement inside an IoT platform, which is called Favorion. Next, let's take a look on simulation result. To test the prototype functionality, I've prepared 3 different water samples, which is a very solid mass, clear water plus solid, and kaolin water mixture plus solid. The purpose of this various water sample are to investigate the signal response produced by the LiDAR across different substrate. Here I attach the result of the experiment, which I want to highlight the signal response of solid plus kaolin water. That gives the most stable signal response, which shows that this system is suitable to be used for shallow water turbidity system, especially in a river. The usage of kaolin water mixture inside this experiment is to mimic the condition of river water, as river water has a suspended particles inside of it and also solid underneath the water. Lastly, let's take a look on the impact and future use. This red laser LiDAR turbidity monitoring system has the potential to bring real impact, especially in low resource area. In agricultural runoff zones, it helps monitor excessive sediment or chemical discharge into nearby rivers, which is crucial for protecting aquatic life and maintaining clean water sources. And because it's low cost and portable, it is ideal for use in rural or underfunded regions where traditional turbidimeters or expensive LiDAR systems are not accessible. As for the future, I plan to integrate solar power to make the system energy independent, test it in real river environment, and work on improving its detection range for better flexibility. Lastly, this innovation could support nationwide water quality monitoring efforts and contribute to sustainable water management using smart and modern technology. I think that's all from me, and thank you for listening.